Good afternoon. Welcome to today's workshop on an introduction to version control using Git for data scientists. My name is Dr. David Pugh. I am a staff scientist at the KAUST Visualization Core Laboratory. And today's workshop is the next in a series of workshops called the Introduction to Data Science Workshop Series that the KAUST Visualization Core Lab has put on, led by myself and assisted by some of my colleagues. To help build capacity in core data science tools such as Conda and Python and Git and SQL here within the KAUST community, and starting to share these workshops via YouTube with the rest of the kingdom and anybody else who wants to subscribe to our YouTube channel as a way to just, again, build capacity in these core foundational data science skills so that we can try to increase both productivity and capability for data science and machine learning here at KAUST. So I'm going to start sharing my screen. Okay. So the first link that I have shared with you before we got started today, and that I will be sure to put in the video description when this goes up on YouTube for those who might be watching the recording, is the link to the GitHub repository for the Introduction to Data Science Workshop Series. So those of you who joined us earlier this semester with for one of the workshops on Conda or Python or Bash, I think those are the three that we've had so far. It's the same repository. I use the same repository for the entire curriculum. Today we're going to be talking about Git. So there's two links that I want to draw your attention to. So the first link is, well, it's actually a button that you can click, which has an embedded link, but it will take you to the KAUST Binder Hub. So I'm just going to copy this and I will put it in the chat for reference. So if you are joining us from within the KAUST, on the KAUST campus or connected in via VPN to the KAUST intranet, then you can click on this link and it will launch a JupyterLab instance that is running all the code and software that we're going to need for today's workshop on top of the KAUST Binder Hub, which has been put together by my colleagues at the IT Research Computing. Now, if you are off of the KAUST campus, or whether you're a KAUST student who's down in Jeddah, or you're just off campus someplace, if you're not connected via the VPN, or you're just joining us, then you will need to use the public Binder Hub. And I'm going to put the link into chat now. So, for instance, I am obviously here on campus, and so I will open in a new tab the Binder Hub, the KAUST Binder Hub, and after a few minutes, well, hopefully not a few minutes, a few seconds, then a Docker container running on top of an image that is built using all of the software and configuration files in the GitHub repo will be launched on IT Research Computing infrastructure on their Binder Hub cluster, and it will be available for us to use interactively. And the same will be true for the public Binder Hub, but instead of running on KAUST infrastructure, it'll be running on public infrastructure, either on Google or infrastructure provided by other research institutes who are part of the Binder Hub Federation. So usually the KAUST Binder Hub is super snappy. It seems to be a little lazy today. So I'm going to also try to open the public Binder Hub. And we will just have a race and see who gets there first. And KAUST wins. So I'm going to close my my public Binder Hub. Okay, so now if I could just see a a show of hands by checking yes. Can you check yes if you've been able to launch JupyterLab using one of the binder hubs and you can see what I'm seeing here on my screen? I'll make it a little bigger so everybody can see it. Okay. So again, like, it may take a little bit to load, so please don't check no if it's just loading. Okay, so I'm guessing it's probably loading for most everyone. I'm seeing a few checks yes, but I've not seen any no's. Okay. Well, while I'm waiting to see if there are any more checks, then I will just talk a little bit about the binder hub interface and things to be aware of. Okay, so today we're going to be covering version control using Git. So even though this is a Python kind of development environment, we're not going to be covering Python today. We're going to be using the terminal and learning Git commands, and we're just using this as a nice interface to get access to a terminal. We're also going to demonstrate a few things as I go along about the JupyterLab GUI that support or that integrate with Git, basically. So we're going to talk about those things as we go along. There is a timeout for the binder hub instances. So if you if you're idle for more than, I think, 30 minutes for the Kaust binder hub, then the cluster will clean up your resources because it thinks they're no longer being used. And I think it's about 20 to 30 minutes for the public binder hub as well. So in order just to make things not be idle, all you have to do is kind of, click. You can double click on a folder or just do something, in some way just to keep it idle. Now, hopefully I won't be talking too much after we get going. So you'll be typing a lot of commands and things like that. And so it shouldn't be too terribly difficult to keep it from timing out on you. Okay, cool. So didn't get a whole lot of participation on that question. Only 6 people bothered to check yes, but I didn't see anybody check no. So I'm going to assume that if you haven't checked yes, that you do in fact have JupyterLab up and running, and I'm going to go ahead and move on and start the teaching. Okay. So now that that's loaded, so what are we going to cover today? So we're going to cover kind of the basics of Git. I'm going to try to motivate a little bit the use of Git for researchers and data scientists. And then we're going to talk about how to set up Git, configure Git, and then all the basics about creating repositories, tracking changes, exploring history. We're going to talk about remotes on GitHub. And then towards the end of the day, we're going to talk briefly about kind of open science, open source philosophy a bit on open science, licensing, citation, hosting, things like that. And then along the way, I will be showing you how you can use the JupyterLab Git integration to accomplish the same thing as typing the Git commands that we're going to learn, but just with clicking via the mouse. Okay. So the course materials that we're going to be using today are from Software Carpentry. So in addition to my position here at Kaust, I am also a certified instructor and instructor trainer with Software and Data Carpentry, and have been for a number of years. So Software Carpentry is a fantastic organization. It's a global nonprofit organization whose goals are to teach kind of best practices for scientific computing and data science, primarily to researchers, but also increasingly in industry. So the lesson materials that we're going to be using today have been developed by the community of instructors and users that have either taught software carpentry workshops for Git or have participated in them and have opened issues on GitHub, and they're developed collaboratively with hundreds of contributors all around the world. So what we're going to cover today is kind of a somewhat contrived example of a collaborative project between two characters, Wolfman and Dracula, who are going to collaborate on a project to write up some documentation about where to send their next planetary lander on Mars and how to get it there. And we're just going to use this as kind of motivation for the files as we create them, and the stuff that we kind of in the files. It's just supposed to be kind of fun and a bit cheeky, and a good pedagogical tool to have this kind of motivational story. So I'm going to teach you how to use version control using Git and to manage this kind of workflow. And then along the way, hopefully you will understand how the same kind of, this tool can be applied to managing everything from papers to source code for your projects to kind of anything in between, anything that can be saved in kind of flat text format, basically. One of the nice things about using a version control system such as Git is that nothing is ever really lost. You have to work really hard or actively do something nefarious to lose work when you're using a tool like Git. Every old version of every file is saved. So it's always possible to go back in time to any particular state of every file or files in the history of the project, as long as you've been using version control since the beginning. Additionally, you always have a record of who made what. And depending if you're good at explaining in your what are called commit messages, which are just little, when you make a new kind of record of the changes on a particular file, if you do a good job of explaining why you made those changes, you will also not only know who made the changes, but you will be able to know why those changes were made. And so you have this really nice record of metadata that explains who, what, and when and why of every change that's ever been made to any file in your project. So this kind of gives you a lot of power. If you're working on a large collaborative project, you always know who you need to go and talk to about particular changes that have been made to files in your project. It also is like an unlimited undo button. Instead of just undoing changes in a Word document, you can kind of go back and forth between different versions from the very beginning of the project to whatever your current state is. It dramatically simplifies the process of working on collaborative projects with multiple people. It can be very easy if you are collaborating by writing in a Word document and then sending different versions of the Word document back and forth via email to overwrite or overlook someone's changes. And then you just get in this loop of sending a document back and forth, and everyone is writing and overwriting their changes, and it quickly becomes a mess. Version control systems like Git enable us to get around that. So even if you don't really work with lots of other collaborators, Git can be very powerful for just you as an individual researcher. You can think of it as like a lab notebook for each of your projects, and it has a complete record of what was done, when it was done, why it was done, and it's very helpful if you have many projects. It helps you keep track of what you've done and why on all your different projects, and particularly if you're coming back to a project after having put it aside for quite a while, it can sometimes be hard to remember why you did certain things. And also, if you get used to using Git and you start using and sharing your code and your projects via GitHub, it's a fantastic way to make yourself known within the open science and research community via the projects and source code that you put on GitHub. Or if you want to contribute to some of the packages that you might use right now as a researcher, if they're open source, they're almost certainly on GitHub. And if they're on GitHub, that means you can contribute to those projects and maybe improve them or fix bugs or add new features. But in order to do that, you will have to learn how to use Git. So by the end of today, you should have some idea of how to do that. Okay. So here's a bit more of a detailed schedule in terms of what we're going to cover and very roughly how long things are going to take. I will try to keep to the schedule as much as possible. We'll see how we get. We'll see how we get on. Okay. So with that, we will jump to the first lesson on automated version control. So this episode basically covers what is version control and why should you use it, and then helps you try to understand the benefits of an automated version control system and the basics of how the system works. So some of this I already have covered, I guess, in the little intro that I just gave, but so I'll move through this quite quickly. So this is this is an interesting cartoon from PhD Comics that summarizes certainly my experience when I was in grad school. I started using Git in grad school as a way to provide version control for all of the software that I was writing for my PhD and for my master's thesis. And I did try to use version control to maintain my my dissertation and share it with my PI at the time, but it went almost nowhere and devolved into exactly this: sending Word documents back and forth for edits and then re-edits and comments and re-edits and comments. And it was crazy frustrating. And so certainly this comic speaks to me. And today what we're going to learn is, at least on your side, how to use Git so that you have an alternative to this kind of a workflow. But of course, you will have to either help onboard your colleagues and your research team, or particularly help onboard your PI if they're not currently using Git, if you really want to completely get out of being in this comic strip. Okay, so roughly the way version control systems work, and the way Git works in particular, is you start with some base version of the document. You can think of the base version of the document as being this version here on the left-hand side, and then you make a change, and then you make a record of the change, and that provides a new document. And then you make another change, and then you store a record of that new change, and that provides a third document. So at each point in time, you're basically snapshotting the document at different states and keeping the changes. And so you can always go kind of back and forth with these different sets of changes. Now, where this is useful, you can have the same base document, and then maybe two users make different changes. And it might be possible that those changes can just be merged together cleanly. So in this case, the one user changed the second sentence in this top paragraph, and the second user added a couple sentences to the second paragraph. Those edits are edits to different parts of the document, so they can actually be merged, and Git will intelligently handle the merging of those changes seamlessly. However, where version control systems are really helpful is in situations where perhaps you have some conflict. So if you have situations where users co-edit or edit the same part of the same document, Git will make it so that it will quickly identify that conflict and then mark it for resolution. Now, there's always going to be a limit to how much you can automate conflict resolution when writing these kinds of documents or developing source code. So at some point, there will have to be a human in the loop to resolve those merge conflicts. And we'll talk about both the automated process and a human process for doing that later. But what version control systems like Git will do is they do a very good job of flagging all of the places where you have these merge conflicts and forcing you to deal with them before you can create a new version of that document, basically. Okay. So I guess to sum up, you can think of version control, if used properly, like an unlimited undo button that you can always kind of move back and forth between the documents in your project and at different states and different points in time. And also version control systems like Git allow people to do work in parallel. So as we'll see, on a team, everybody might have their own copy, local copy of the source code that you're working on, and you have mechanisms for, making progress independently as long as you're working on parts of the project that no one else is working on and sharing your changes in an efficient way with everybody else. And then if two people happen to work on the same part of the project and try to share those changes, Git will flag it as a conflict. And then those two individuals can quickly get together and figure out either if it's source code, whose version is the more correct version that should be used, or if it's a paper that you're working on, you can have a more kind of extended discussion about who should take charge of that section for writing the paper. Okay, any quick questions either in the chat or in Gitter, or if you want to unmute yourself and ask a question about the basics of version control or the motivation for version control, or maybe you have an idea for if you're uncertain about whether a use case you have for version control might be appropriate, you could ask those kinds of questions now. Otherwise, I'll just move on. Okay. Not seeing any questions. Oh, can we use it with Overleaf? So that's a great question. The answer is yes. So Overleaf, so if you're, just in case you're not familiar with Overleaf, Overleaf is an online LaTeX editor for collaboratively writing documents and papers in LaTeX, which is a typesetting language. Very commonly used in academia, great for typesetting mathematics equations. And lots of people are using Overleaf now because it makes it really easy to work collaboratively on these LaTeX documents and to share or actually submit journal articles in many cases. So Overleaf actually uses Git behind the scenes to provide version control for your paper. And it kind of abstracts from the details of using Git to do that, but that's what it's using behind the scenes. And I believe if you have, like, for example, a source code repository, is relevant for your paper, you can integrate the two Git repos so that they're aware of one another. I don't exactly remember the details of doing that off the top of my head, and it's a little bit out of scope. But yes, you can use Git and GitHub and Overleaf together. They're very closely related in some respects. So thank you for asking that question, William. Okay, any more questions? All right. So I'm going to move right along. Okay, so at this point, I am going to switch to, I have my teaching notes up on a second screen. And so I'm going to switch back to Jupyter Lab, and we'll predominantly be using Jupyter Lab, or I'll be sharing my Jupyter Lab screen and doing hands-on stuff at this point. So the first thing that we need to do is we need to set up Git. So in this episode, we're going to cover how to set up and use Git. In particular, we'll talk about how to configure Git the first time it is used on a computer, and then talk about the Git configuration files and the difference between a global configuration file and a project-specific local configuration file. Okay, So when we use Git the first time, there are a few things that we need to configure. In particular, we have to provide a username and an email address. The username and email address will be used to mark every commit that is made by that particular user. And that way, there's always a who and a point of contact for every change that has been made. So that's the first thing that we're going to do. So we're going to start by working in the terminal today. So down here on the Jupyter Lab interface, if you just click the terminal, you should be taken to a terminal screen. It should look like this. And if you type print working directory, PWD, then you should see that you are in this user's home directory. So this is not, even though this is running on Cal's infrastructure, this is not a Cal's username. This is a user inside the image, inside the Docker container called Jovian. It's just for teaching purposes. But we're going to be working here in the terminal for most of the day. Okay, so the first command that we need to run is Git. So Git is the name of the program. This is the version control program that we're going to be using. And the command is config. And if we type --help, oh, right, yes. Okay. We'll have to, the help menus are not on this image. So we'll have to resort to the teaching materials. So the commands are going to come in the form of Git, which is the version control program. And then there's going to be a command, which you can think of as like a verb, which is the thing that we want to do. It's not always a verb. Like in this case, it's not a verb, really. And then there's going to be some options. So in this case, the first command that we're going to want to use is Git Config. And then we're going to use the global option to set the username to be Vlad Dracula. And there's a note in the config-h. I wonder why the --help didn't work. Interesting. So here is the help menu for the git config command. Thank you for pointing that out, Luis. So you can see it talks about the different config files. So the global config file, which is the configuration file for Git that will apply across all projects, is the one that we're going to edit. And then there's some other options and things that you can do. But basically what we want to do is we want to run this git config command to set the username to be, in this case, we'll call it Vlad Dracula, in keeping with our little motivational story. Okay. So now I'm going to type a command called clear just to clear this out. And so we ran this command. And now we're going to run git config to set in the global configuration the user email. Now, you can, this email, once we start using GitHub, so this email will be plastered all over GitHub. So you should either use an email that you're happy with being made public, or there is a special email address, which is included here. It's just username@users.noreply.github.com, which you can add as your user email, which basically obfuscates your email, and therefore anybody who wanted to contact you would have to have some other means of contacting you about whatever change that you're doing. So it's up to you. In this case, it doesn't really matter because we're just going to use this made up email, Vlad@Transylvania. Okay, so now that we have we've set these two configuration values. So again, these just want to reiterate that these configuration options because we've passed the -- global option, these configuration values will apply to every Git repository that we create on this computer. They can be overridden at the repository level by altering what's called the local config. And we might see some examples of that. Okay. There's a couple of other things that that I want to set. I want to point out. So the other is line endings. So this is especially important if you're going to be working on a project where your colleagues have different operating systems than you do. So Mac and Linux are Unix-based operating systems, so the same kind of hidden character in text files that encodes a line ending is used on both of those operating systems. Windows is not a Unix-based system and has its own special character for denoting a line ending. And if you are collaborating with colleagues that have different operating systems, every time your colleague who runs Windows opens a file that was written on Linux, Windows is going to automatically replace the Linux line endings with the Windows line endings. And then when they commit their changes and upload it, you're going to pass the Windows line endings back up to your repository that you might be sharing. So this is a bit of a mess. And the way that you avoid that is by setting your configuration. If you're on Mac or Linux, you copy this first line. And then if you're on Windows, you copy the second line. And then that will allow Git to basically convert Windows line endings automatically to Unix line endings so that they're always in common when you're working with collaborators. So we'll just paste this. Since we're all using Linux, we will paste the first option. So we hit enter. And all of this only has to be done once. So this is where we're configuring Git from scratch. So it only has to be done once. So the next thing is you might have a favorite text editor. So when we write messages to ourselves, like little notes to ourselves, when we record a set of changes using Git, we have to do that in some kind of a text editor. And so then the question is, well, which text editor do we want to use and whatnot? And so you can configure that here with Git. So for the purposes of this training, I'm going to use a simple terminal-based text editor called Nano. But in practice on my own work, since I often develop in Microsoft Visual Studio Code, I typically would set the config to VS Code, which is at the bottom. Now, text editors are very much a personal preference, and your favorite text editor might be listed here or it might not be listed here. If it's not listed here, then you could do a little Googling about and probably find the correct Git config setting in order to enable that, your favorite text editor as your default text editor. If you don't have a favorite text editor, I would strongly recommend Microsoft Visual Studio Code. Okay, but I'm going to make Nano for the purposes of today. Okay. Now, because everybody has set Nano as their default text editor, you will probably not find yourself getting stuck in the default setting for text editor, which is Vim. Vim is a very powerful terminal-based text editor with a huge learning curve. And as you might expect, if you get stuck in Vim, the way that you get out of Vim is by typing escape and then :WQ and hitting enter. So if that is the level of complexity required to simply exit from the text editor itself, you might imagine the level of complexity required to do more sophisticated things. So we're not going to use Vim, but there's a little tool here to tell you how to get out if you do in fact get stuck in it. Okay, so we've changed a lot of things, and we might wonder, well, how can I look at my config to see what it actually is? So if we do git config global and then list. Oh, indeed, config is not a command. Okay, so this, what I've done here is basically listed out the configuration that we've set, or the configuration file that we've created. And so you can just see here all of the configuration options that we kind of manually entered. Now, okay. So in the teaching materials, there is some notes about proxies, which aren't important for us here. And again, the help command, it will be git, and then whatever the command is. In this case, it was config. And then -- help does not seem to work, but -h works. So if you ever want to read the manual on the whatever git command we're working with, then just try -h and then hit enter, and it should all work as expected. Okay. So any quick questions on the process of setting things up on Git for the first time? And this is something that you only have to do once. So here we're working in a cloud-based instance, so we're going to have to configure it. But once you install Git on your local machine and configure it, you only have to do that once. So any questions about the configuration, either in the chat, or you can unmute yourself, or on Gitter. Okay, so moving right along. Okay, so creating a repository. So in this episode, we're going to cover we're going to talk about where Git stores information. So I've been talking about all these copies that Git stores and all the changes that Git stores. So we're going to talk about where's that information actually stored, and we're going to see how to create a Git repository. And then we will describe the purpose of the special.git directory. Okay, so we're going to continue with our little story of our 3 characters here, Wolfman, Dracula, and the Mummy, and their attempts to set up a interplanetary base on Mars, the Moon, and Pluto. Okay, so the first thing that we need to do is we're going to create a directory for our new project. So we're going to have a new project, so we need a new directory. And we're going to create it not on our desktop, on our local machine, but rather we're going to create it inside this introduction to Git. So if you go all the way back to the kind of the root of the repository that we're working with, if you click on Introduction to Git, and then at the top, there's a little icon that has a plus and a folder. If you click on that, then you can type, create a new directory called planets. Now, similarly, from the terminal, I'm just going to type clear to clear this out, and pwd. So in our home directory, if we were to change directories into the introduction to Git, and we run a listing, we can see that the planets directory is there. We could have run these commands and then typed make dir other planets if we had wanted to create a directory via the terminal. You can see there's the other planets directory. Okay, so we have a new project, we're gonna have a new directory. And so now we need to change into our project directories. So we'll do cd planets. And you can see as I change, this is a very, very, very long username and host, but then the file path and the prompt tells me where I am in the file system. So you can see them in the planets directory. And now if I type the command Git Init, this initializes an empty Git repository in the current directory in which this command is executed. So when we hit enter, it says initialized an empty Git repository in home, Jovian, introduction to Git, planets.git. Okay. And there's a hint that this .git special directory is indeed special, and we'll come on to that in just a moment. Okay. Now, if we type, after we've run this command, if we were to type ls and hit enter, it looks like there's nothing there. But if you remember from the bash course that I taught earlier this term, or you have some familiarity with bash, files and directories that start with a dot are what are called hidden files and directories. And so in order to see those, you need to pass the -a option to the ls command. And so there we can see now we actually have 3 directories. We have dot, which is a reference to the current directory, dot, which is a reference to the parent directory, which would be, in this case, introduction to Git, and then this .git directory. Okay, and so this is a hidden directory, and long story short, all of your, the contents of your repository, all of the record of changes and versions of the different documents and files are going to be stored in this .git directory. So as long as that .git directory is around, you can always recover all of the, you have your unlimited undo button. If anything were to happen to this .git directory, then that would be very bad. And we'll come on to that in a moment. Okay. Now, just for a moment, I want to talk about a couple of features in JupyterLab that are related to this part of Git. So over here on the left-hand side, here at the very top, you have your file, which basically just toggles the file system viewing pane. And then down here, you have this little Git icon. And if you click on that, you will see that you get all of this information about some Git repository. And this is actually not the Git repository that we just created, but it's the Git repository that was used when this whole cloud instance was created. So what we need to do is get our the repository that we just created working. And in order to do that, we need to navigate. There we go. So in order to get that to work, you need to, sometimes it will just show up, I guess, and sometimes you might have to go through a correct sequence by starting at the very root of your file system and then going through. So you click on this little folder and then you go introduction to Git and then planets, and then click on the Git plugin button, and that will load this viewer into the current Git repository that we created. So I just want to check if everybody has managed to do that or not. So I'm going to clear. So if you could just check yes, if you were able to get this on the left-hand side here where you have current repository, it should say planets, and in current branch, it should say master. I just want to check to make sure that this Git plugin for JupyterLab is working. Okay, and again, if you click on the folder and then go back to the root of the repository and then click on introduction to Git and then planets and then click on this, then it should work. Okay, so I'm seeing mostly yeses. I don't see any no's, so I'll assume that everybody's got it to work. Okay, cool. So for the rest of today, I'm going to keep the terminal open, and I'm going to keep this kind of GUI interface that integrates with JupyterLab into the repository open, and I'll show you how to do the same kinds of things either with the Git command manually or with kind of using your mouse to click different buttons and things over here. Okay. So let's go ahead and run my most often used Git command, which is Git Status. Git Status. So this tells you kind of what the current state of your repository is. So this is the command you will run more often than any other command, because you will often want to know, what is the current state of my repository? What files are not yet being tracked for changes? What files have changes that I need to store? And what files have changes that have been grouped together and are ready to actually save formally? But we don't have any of those yet. We don't have any files or anything in this repository. We just have a completely empty repository. Okay. So that's this episode done. So this episode was basically about initializing an empty Git repository, both manually and then in Jupyter Lab, seeing how you can navigate to this new repository that we've created. And are there any questions about that? Okay, so there's a couple of exercises here that I'll just talk through the solutions, and then we'll move on. We can do some hands-on exercises later. So the first exercise is about whether you should have a Git repository inside another Git repository. So, if we wanted to create basically a directory called moons inside our planets directory. So for example, if we did make dir moons, so now we have this moons directory. Do we then need to go into moons and run this git init command again? And the answer is no, we don't. We don't want to do that. We don't need to do that. It's not a good idea to do that. So once you have initialized an empty Git repository in a directory, that will enable you to version control all files in any subdirectory or subdirectory of subdirectories and so forth within the directory in which you ran the git init command. So if you accidentally do something like what I just did here, which is create a Git repository someplace where you didn't want to create it, then the solution is to basically just blow away this .git repository. And the way that you do that is you use this rm command with -rf, and then always good to check where you are before you run this command. So I'm in the moons directory, and I want to remove the .git directory, so I can do remove .r for recursive and f for force, which means don't warn me or anything, just do it. Just delete this directory. And so now that has completely removed that .git directory. So I mentioned this in the bash course. So this is a very powerful command, rm-rf. It will completely delete everything in a directory and any subdirectories and sub-subdirectories and so on and so forth. So this .git directory is now gone, and it was empty, so that's fine. Like, it's not like we made it an error and therefore we wanted to delete it. But this would be a like actively nefarious bad thing that if you did this on a Git repository that you actually cared about, you might lose work. And I say only might lose work because if you are using Git and then a remote repository like GitHub or GitLab to have the kind of the master copy of your work, then that repository that is stored on the remote server will still be there, and you can recreate the repository on your local machine even if you've completely deleted it. Okay. So any questions about the process of initializing a Git repository? Okay, So we'll just keep moving right along. So those first two episodes were about the basics. This next episode is getting into kind of the meat of working with Git, which is how do you record changes in Git? What are the commands? And what is the process for making and recording changes to Git? Okay. So in this episode, we're going to talk about how to record changes. We're going to talk about how to check the status of your version control repository with this Git Status command. We're going to see how to use that at different stages in the process of adding and recording changes. And then we're going to talk about the importance of making notes about the changes that you're recording. And then we're going to, the basic objective is to show you how to go through this modify, add, commit cycle for one or more files. And we're going to quite slowly go through this cycle, even though in practice you might go through the cycle in about 30 seconds when you're actually working with Git. But you need to understand kind of what's going on at each point in this cycle so that you know what you're doing when you're kind of moving quickly with Git. Right, okay. So here we go. So I'm just going to type clear and change directories. So we're going to make a text file. And the way that we're going to make this text file, instead of using Nano, which is the terminal-based text editor, we're going to try to minimize using that as much as possible. So we're going to take advantage of the fact that we're using JupyterLab and navigate to our planets directory. And then we'll do File, New, Text File. And then if you right-click on the file, you can rename it, and we'll call it mars.txt. Now, if you follow along with the commands and the teaching notes, it'll teach you the terminal commands to kind of create and edit a file. But I'm going to do that with JupyterLab interface to take advantage of it since we're using it. So what we want to do is we've created this text file. And now if we run ls, we can see that we have this text file, mars.txt, in addition to this directory that I created previously. And we want to add some text. So, so some basic notes, just some text about Mars. So it is very cold and dry, but everything is red, which is my favorite color. Something like this. It doesn't really matter. We've made a modification change to the file that we want to record. So now we've saved this. Go back to our terminal, and then we can go back to our Git indicator here. Now notice we've created this file, and now we see there's a file down here called mars.txt, and it's listed as being untracked. That might suggest that it's not yet been tracked by our version control system. So if we type Git Status and hit enter, now we see a different message than what we saw previously. So we're still on the master branch. We still have no commits, but now we have untracked files. And you can see the mapping between the information that is listed here in untracked files and the information that is listed in the JupyterLab Git plugin as being untracked files. And the untracked files are listed in red indicating that this is bad. They're not version controlled. You should consider version controlling these files. Now this directory.ipynb checkpoints, you can just ignore. It's an artifact of JupyterLab's own kind of built-in mini version control system, but we can just ignore it for the purposes of today. We'll talk about how to actually ignore it in a later episode. Okay, so we want to, now that we've made some changes to a file, we want to stage these changes. Now, staging changes is and we're going to do that with, I'll show you the command first. We're going to do that with a git add. So this is the second stage. So we went through the modify stage. So we made some changes to a file. Next, we're going to go to the add change. So we're going to add stage. We're going to add those modifications to the staging area. So we git add, and then the name of the file that we want to add. And so now if we run git status again, we'll see we still have this kind of directory that we can ignore, this IPy NB checkpoints directory, but now we have a green file, a new file, mars.txt. So we have added that, new file and its contents to the staging area, but it's not yet been committed. And similarly, over here in the plugin, you can see that the file was previously untracked. It's now moved to the staged area, the staging area. So we've told Git that it needs to keep track of this file, mars.txt, but we haven't actually recorded the changes that we made. So in order to do that, we have to do the final stage of the modify add commit cycle, which is the commit. So we do git commit, and then we have to provide a commit message. And you must always provide a commit message. And the commit message is like a note to both yourself and any collaborators or future users of your code or your project as to why you made these changes. So, a simple commit message for starting a new file might be something like started taking notes on Mars as a base. And note that the commit message when we're typing at the command line is -m is the option, followed by double quoted string, which is the commit message. And it should be very short. Here the commit message is almost as long as the change itself, but that's rarely the case. But it should be pretty short, maybe 50 characters or so is a good rule of thumb. And then you hit enter. And now we see a response. So we see that we have a commit, and we have one file has been changed, and there's one line of inserted text. And then a file was created with, these are permissions, we don't need to worry ourselves with those today. And it's called mars.txt. Okay. And notice now here, our file that was in the staging area is now empty. And if we click on the history, we'll see that basically this information here is now showing up in the history. And as we do more commits and we make more changes to files, we're going to build up this history of committed changes. And it's that history that we can use the power of version control to kind of move back and forward to any particular stage or point in time in the history of our repository. And we'll see how to move back and forth and in future episodes. Okay. And we can see there's a command called Git Log, which shows you basically the same information that they're displaying here in the history. They're pulling this information from this Git Log command. And we'll run this command after we've made more commits, and we'll see how this Git Log kind of builds up. So it will list these commits in reverse chronological order. So the most recent commit will be listed first, all the way back to, at the very bottom, you would find this commit, which is the very first commit we made on the whole repository. Commits are generally small changes. So if you look at like a repository on GitHub that's been around for many years, and it's been worked on by many, there could be tens of thousands of commits easily made to a really large project with lots of contributors that's been around for a while. Okay, so where exactly are these changes? So I'm going to run clear just to get this out of the way. And then if we run ls, so we can see here's our Mars, our Mars.txt. So the changes and the information about the changes and all this metadata that I talked about is stored in the .git directory itself. So what you will see in your current working directory is the most recent version of the files that you're working with. All of the changes in the previous versions will be stored in the .git subdirectory. And when we talk about moving back and forth between the current version and older versions, effectively what will happen is that when you move to older versions of files, Git will reach into the .git subdirectory and pull out those older versions of files and replace the version in your working directory with those older versions. And then you can kind of move back and forth like this. Okay, so we're going to go through this again. So we're going to go to Mars.txt, and we're going to hit, go back over here and click on changes so we can watch this modify add commit cycle at work. So we're going to go to Mars.txt and we'll hit enter, and we'll add another line. The 2 moons might prove problematic for our friend Wolfman. Okay, and now, so we've made these changes. As soon as we save them with maybe a Control S, or you could go up here and File and Save File, Command S. Now you can see Git detects that Mars.txt has changed. It detects that this line has been added and now the file is different. And if we go back to our terminal and we type Git Status, we will indeed see that there is a modified file called Mars.txt. And Git tries to give you hints about what commands you might want to type next. So it tells you if you want to add the modifications to the staging area, then you should use the git add command. If you don't want to do that, if you want to kind of undo the changes to that file that you made, then you can run this Git Restore on the file, and it will return it to the previous version. So it basically delete the second line that we just added. Okay. Now, there is another command that's useful to know that is called Diff, and it's short for difference. It shows the difference between 2 files. In this case, it's going to show the difference between the most recently committed version of a file and the file that is in the current directory, the file that has been modified. So if we do git diff mars.txt and hit enter, then you get status. Sorry, I'm just checking. Right. Okay. So we run git diff, and it shows us the changes that that exist. Okay, and you can run it without the file name if you wish. So over here in the Git plugin for Jupyter Lab, if you kind of hover over the file that's been changed, you can see that there are little buttons over here. One will open this file, the other will diff this file. So if we do a diff on the file, it basically gives you a graphical representation of the changes. So you can see here on the left-hand side is the original version, on the right-hand side is the version where with the changes that we have made. In this case, we've only added things, so you get this green line here. So go back to our terminal window. I'm just going to clear this out. Okay, so we still need to go through. So the lecture notes have some more like really detailed information about what is the information, the metadata in the Git Diff output. I think I've covered all of what I want to cover with that. So what we need to do now is add our changes. So we've made our modifications. Now we'll do git add mars.txt. And then we do git. So once we've added these changes, so again, we've moved our file from being changed to now we've staged these changes. And now we're going to commit them. So we do git commit, and with our commit message, and actually what I'll do is I'll show you how to do this. Instead of from the terminal, I'll show you how to do it over here. So if we select this file, mars.txt, and we come down here, and now we can type our commit message here into this text box here. So we can type, added some concerns about the moon impact on Wolfman. So we can type our commit message in here, and then notice as soon as we type something, the commit button lit up. So you can't commit anything without a message. You have to actually put a commit message of some kind for every commit that you make. But now if you click commit, it'll commit the changes, and then it'll say, oh, we've committed these changes. And if you look at the history, you'll see now there are 2 commits. There was the original commit, and then the one that we just made. And now if we go over here and we were to type git status, we see that we're on the master branch. We have no untracked files because we committed. It's as if we had run git commit and then the commit message here, and if we had typed it in manually, basically. Okay. So we've gone through this modify, add, commit cycle a few times now. You might be wondering, like, what's the point of having this staging area? Like, why do we have to add the modifications to the staging area before we commit them? Why can't we just like directly commit them into the repository? And the answer is that often you're going to want to make make changes to multiple files at once, and these changes are logically related to one another. And if you would want to undo them, you would want to undo them together. In that case, you can add multiple sets of changes on different files to the staging area, and then commit all of those changes at once. So the staging area allows you this really fine-grained control over over how to group the changes that you make to the files in your project in a logically coherent way. Okay, and that is what is covered in the staging area. Sorry, I've lost, here we go, in the staging area here. So you can think of it like this. So the file here on the left-hand side is what's actually in your working directory. And then everything in this gray box is what is in the .git directory. And when you add changes from one or more files into the staging area with git add, you're kind of moving those changes inside the .git directory into the staging area. And the staging area could contain maybe just one change, like the 2 commits that we've just made, or it could contain many changes in many files. And then when we do commit, we basically take the contents of the staging area and we add it to the repository on the top of the stack. And you can think of the repository as a stack. So a stack has the structure that kind of the last thing that you put onto the stack is the first thing that's going to come off of the stack. And that's the way that the changes in the repository are stored. So our very first commit that we make is going to be at the bottom of the stack. And then every commit after that is going to be another layer on the stack, basically. Okay, so we're going to do this, I think, one more time. So let's go and add another line to our file. So we'll add, but our other friend, I can't type today, the mummy, will appreciate the lack of humidity. And then we'll save. Okay, so now we've added this third line. And as soon as we hit save, our changes show up as the file is changed over here. And if we run Git Status, we can see that we have these changes and we need to add them. And if we were to run Git Diff, we'll see that we have the difference between the current file and the changes in the most recently committed version. So now we need to do git add mars.txt. Now if we run git diff, we don't see anything, because once you've added the changes, then you've put the changes inside the .git directory. Again, looking here. So once we've done git add, everything is in here. And so when we run the diff compares the version here that is in the directory with the version that is the most recent version in the .git subdirectory. So that could be in the staging area if you have changes that are staged, or it could be on top of the repository if you don't have any changes staged. So that's why when you run git diff, you're comparing the same file, or there's no changes basically to show. So that's why you don't get any. If you want, there's an option that you can do git diff, and then you can pass staged, which will kind of compare the most recent version that's been committed with the version that has been staged. And then you'll see that you can get that kind of same answer again, basically. Okay, so but now we want to commit. So I'm going to clear this, and then we'll do git commit. And then discussed issues with climate of Mars or the mummy. So there's our commit message. And then you can see in our history, we have a third commit in the history. And if we were to run git status, we don't have anything to commit, or we have nothing to commit. Our working directory is clean. And then we could run git log again if we wanted, and we could see the same information, these commits in reverse chronological order, from the most recent to the very first commit in the history. Okay. There's some kind of interesting notes in or call out boxes in the teaching materials about how to do word-based diffing. So you may have noticed that the diffs that we've been looking at have all been comparing lines. It's like this line was added, this line was deleted. If you want more fine-grained control, you can actually get it to highlight what words in the same line are different. This might be more appropriate if you're doing version control on a paper that you're writing, where kind of the words changing within the line might be more important, whereas if you're doing software, it might just be the most important unit might be that single line of code. when the log gets really long, you can press spacebar basically to toggle between through the pages of the log, and you can press Q to get out of the log. I'll talk about that again as our log gets a little longer. If you want to only look at certain number of most recent commits, then you can use the Git Log and with a number. So if we only wanted to look at the most recent commit in the log, we could do Git Log with a 1, I think, or 2 to get the most recent 2 commits, and so forth. There's quite a lot of stuff that you can do with the log. Honestly, I usually look at the most recent like 5 commits in the log, and that's about it. I don't do a lot of super detailed stuff with the log. Okay, a useful note about directories. So Git version controls files, not directories. So if you have, like in this case, we have, I'm going to clear this out now. So we have this directory moons, and moons, even though we created it ages ago, is not shown up at all in our modify add commit cycle. Like Git is not asking us if we want to add this moons directory. And that's because Git doesn't add directories, it adds files. So if you want to create an empty directory in your repository, which I sometimes do, I create a lot of template repositories to help users here at Calus get started with data science and machine learning. So I like to have my projects structured in a certain way. So I'll often put a placeholder directory that I expect somebody to actually populate with results or with data or with source code when they actually use the template for the project. You can add a file called .git keep. So you can just create a completely empty file in a directory. So if we were to use this command called touch to create an empty file called .git keep. Now, if we were to run Git Status, Git now sees that there is effectively a file in this moons directory. And we could do git add moons.git keep, and then git commit. And our commit message could be something like created placeholder directory for moons. And now we can look at our log. And now if we do git status, then we can see that this moons directory that was untracked is now being tracked. Okay. So here's just a nice recap of what would happen if you had multiple changes or changes to multiple files in the same commit. So we make some changes to this first file in green, some changes to the second file in purple, and then we add file 1 and then add file 2. And so the staging area would now contain 2 files. And then when we do the commit, we would take those changes and add them to the repository. And then if we wanted to undo those changes, we would have to undo them together. So undoing the most recent changes would undo both the green and the purple changes in those 2 separate files. Okay, so we've been going for about an hour and a half and covered a lot of ground. So I think now is a good time to take a 10-minute break. I'm going to take a break for 5 minutes, and then I'll come back and see if anybody has questions or whatnot for another 5 minutes before we move on. If you want some practice with some exercises, so there's some discussions about commit message, and then kind of walking through and trying to understand if you understand the correct sequence of Git commands that you need to use to successfully stage and commit the changes to a particular file. So, and I guess I should wrap up before we take a break. So we learned the three most important commands in this episode: Git Status, which shows you the state of the repository; Git Add, which is used to put modified files into the staging area; and Git Commit, which actually stores the record of those changes to those file or files and then adds it to the new local repository. Okay, so I'm going to stop my screen sharing for the moment. So we're going to take a 10-minute break. I'll go away for 5 minutes and then I'll come back again, and then I can take questions for a few minutes before we get started again. So I'll see you in about 10 minutes or so. I'm going to go ahead and pause the recording now. And so if anybody has any questions, we can take 5 minutes. I can answer any questions that you might have before we move on. Just go ahead and set a little timer for myself to keep me on time.
David, I have a question.
Yes.
Is this .git folder blind to where it is? So can we move it to another place if we want to change the working directory for the local project?
Yes, that's perfectly fine. You can so you can move that .git directory around, and then wherever you move it to, you change the name of the project directory, for example. I do this quite frequently. Then, once you're inside that directory, then when you're running Git commands, Git is referencing the .git directory, and it doesn't know or have any need to know kind of what's going on in the file system above the directory that contains the .git directory.
Okay, good, thank you.
So there's a question in the chat about how to manage 2 Git accounts in one computer. So it's a very good question. The way that you do this is with keeping track of your global versus local configurations. So presumably on each project you're working on, you will have one kind of Git account or Git username and contact for that project. So what you can do is on your for the local configuration for that environment, you can do Git config and your username and Git config and your email without the -- global option. And that will set the values for the username and the email for that Git repository to a specific user. And then anything that's set with the -- global option applies to all repositories unless it's overridden by something that is set in a local configuration. So basically, if you just run the same commands that I showed you how to run at the beginning of this training without the -- global, then that would be how you could override the user and the email for the current repo that you're in, basically. So you manage it at the repository level. So if you had 6 different projects and you wanted to have 6 different usernames and emails, one for each of those projects, you could do that just fine. Typically what I do, first I try to basically keep my work development separate from my personal development on separate machines. But here at KAUST, part of my job is to contribute to open source projects. And so some of those contributions are made as, me as my KAUST Git account, and some of them are made from my personal Git account. And so I keep kind of my global configuration set on my work laptop using my KAUST username and my KAUST email. But then I will override that on some projects that are where it's better for me to contribute as my personal GitHub account and my personal email, then I will override the local config appropriately. So that's a good question. Any other questions? So the question is in the chat, is this the only goal of the staging area to commit many files together? And there might be other reasons for the staging area, but that's the one that I think is the most relevant to understand. And that's the one that I think about, is that if you didn't have a staging area, then every change would kind of have to be committed, and there would be no way to group changes that were logically related together and make one commit with those combined changes. Okay, any other questions before we move on? Okay, cool. Well, let's just pick up where we left off then. So I will start sharing my screen again. Okay, cool. So we finished the previous episode, and now we're on exploring history. Oh, wait, there might be one more in the chat, maybe. So Laurent has a question that, what happens if we stage some changes, forget to commit, and then change the file again? So probably the best way to answer that question is to just demonstrate that. So, so how would we do that? So let's clear. So let's go over here to Mars, and let's make, we'll start some change that we are going to add, but then forget to commit. All right, so we'll save that. And then over here, we'll look at our changes. So we can see that there's been this change, that there's been this modification. And let's go ahead and add. So we can either click on this plus button to stage the change. So that's the same as running git add on mars.txt. So we'll modify it, okay? And then we'll come back over here and say we forgot to basically commit. And so we come back over here and we do, we hit enter and say, now I am making another change to the file without having committed, without having committed the previous change. So we'll save. Okay, so now you can see that we have changes. We have Mars that has changes that are staged and changes that are showing up as changing. So if we do Git Status, okay. So at this point, we can either go ahead and run Git Commit, in which case it will commit these previous changes that we made. So if we were to do, I guess we have a decision. So we can say, okay, I forgot to commit these. I could just do Git Commit, committing previous changes, something like this. Yeah. And now if we run Git Status, we'll see we have these modifications. And then if we were to look at the Git log, so we have, here's our log with the previous changes. And now we only have this new change that we made that we hadn't added. So that's one way that, so basically, there's no big deal if you do that. You can either choose to just go and commit, run the commit again, and it will commit only those changes that you had staged, or you could have and we'll see an example of how to do this in a minute, you could have unstaged those changes and then restaged the two changes that we made together and then committed. It kind of would depend on what you wanted to do at that point. Okay, good question. So let's pick up with exploring history. So in this episode, this is kind of like, there's really kind of 3 core episodes today. Like one we just covered. This is the second one. The third one is on remotes in GitHub, which we'll cover is, I think, the episode, not the next one, but the one after that. So in this episode, we're going to talk about how to identify old versions of files and how to review changes and recover old versions of files. So like this is how the undo button works when you're working with old files. And to do this, we'll have to talk about the head of the repository, kind of what it is and how you use it, and then how to identify and use Git commit numbers and whatnot. So, and the idea is that after this episode, you should understand the commands that you need to run in order to undo changes that are undesirable for whatever reason. Okay. So let's go back here. So the first thing we need to do is we need to make an undesirable change. So I will go ahead and add a third paragraph. And so here we will make some very ill-considered change to our file. And we'll save it. Okay. All right. So I'm going to clear this out. And so now if we do git diff mars.text, well, let's actually clear this out. So let's look at the diff over here. The diff. So I've actually just done the thing that Laurent asked the question about, I think. So let's check the status. Oop. No, so it's not quite that. So I made, I never added, this. So I added this change and then forgot to commit. And then I made this other change. And then I was like, oh, right, I forgot to commit that previous change, which is no big deal. So then I committed this change. But now I have these 2 lines here, which are modifications to the file and haven't been added yet. So that's why when you look at the diff, it's showing these 2 lines as being added. So why don't I do this? Since I've spotted this, I'm just going to cut this out. And I'm going to go ahead and just commit this previous change. So I will do git add mars.text git commit. And then this was finished the partial commit from earlier. Okay. Now I can run git status, and I can see that on branch master, and I don't have any untracked files. Okay. So now let's add our very ill-considered change. And now if we run git status, we can see that we have this change. And if we come over here, we can look at the diff, and now we only have this ill-considered change, which is what we want. So I'm going to clear this out again. So in the notes, they show you how you can, the git diff command automatically compares two versions of a file. And normally we had either been either not specifying which file we wanted to diff, or not specifying which two versions of the file we wanted to compare. So if we want, we can specify to compare the diff between the head of the repo and the current version. So the head of the repo is going to be kind of the top of the stack of the repo, and the current working directory of the file mars.txt. And when we do that, we see that, okay, here is this ill-considered change. So it's the same kind of information we got from this, comparing this visual diff in the Jupyter Lab plugin. Okay. So if we wanted to compare relative to the head, if we wanted to go the next change down in the stack, we can do head tilde 1. So that's one change before the head, and compare with the current version of mars.txt. We can do that. And when we do that, we see that we have the ill-considered change, and then let's look at our history. See this. So this is the most recent, and this is the next most recent change. So here we can look at the diff for that one. No, that's not quite what we want. So this is basically going one change before that. And then we could keep doing this and go 2 changes back, 3 changes back, by just kind of going through like so on and so forth, until eventually we would get all the way back to, so I guess if we look at our history, so we did 1, 2, 3, 4, 5. So we've made 5 commits so far. And I guess this counts at 6. Right, okay. So if we go back 6, we've gone back too far, and we hit this kind of fatal error that there is no head tilde 6 version, because there are too many, we've gone back too many commits. So if we go back to head tilde 5, then we'll basically get a representation of all the changes that we had made. So basically we had added all of these lines. Okay. So this head tilde syntax is how you kind of go back and forth. In the lecture notes, I mentioned a show command. So let me clear this out. A git show command, where you can kind of compare the difference between head tilde 3, say, and mars.txt. So this should be the same information that you get if you went 1, 2, 3, and then looked at. So this is head tilde 1, tilde 2, tilde 3. This one should be the same information that we got here. But that's not quite lining up the way that I was expecting, or it's not displaying the information the way that I was expecting. Well, let's go with the the information that's being shown here with the show command, because that is showing what I was expecting. Okay, so that's git show. You can compare in the teaching notes. It shows you how to compare using Git Diff with something called the commit hash. So every commit is given this. It's given its unique identifier, which is this this code here. So every commit in a repo will have a unique identifier, and you can always that always allows you to compare the version of the file or files in your current working directory with a particular version using this unique identifier. So, we could copy and paste this identifier and do git diff with this identifier, mars.txt, and that gives us the same information. So you can either use this kind of head tilde syntax, or if you find the head tilde kind of sometimes hard to remember where you are, you can always use this unique identifier, and you actually don't need to use the entire thing. You actually just need to use enough to make it identifiable. So typically, like, the first 8 is probably enough. So if I do git diff mars.txt, yeah, that's enough. So you usually only have to put the first few characters, and you can see that in many cases on Git will truncate this to the first 7 or 8 characters usually. Okay. So basically, that's how you refer to different versions, by either this, commit hash, or this commit identifier, or this head tilde syntax. So I'm going to clear this out. So let's run git status and see where we are. So we have this this ill-considered change, but we haven't actually added it or committed it yet. So what do we want to do? So let's say at this point, we figured out that we've made this ill-considered change before we've added it or before we've committed it. So then what do we do? So in the lecture notes, I think the lecture notes are using a slightly older version of Git than the one that I have installed here in the in this instance. So the previous command was git checkout, but if you use an older version of Git, git checkout is used for everything. So it's nice that in newer versions, they've changed the command, improved the command to do this. So if we do git restore mars.txt, yeah. So that's the kind of the hint that Git gives you. It's like you either add these changes to the staging area, or you run git restore and the file name. And now if we go and look at the file, it should, yes, okay. So if we go and look at the file, I ran this cat command just to put the version of the file on disk and print it to the screen. You can see that the ill-considered change is gone. And now if I was to go back to changes, and now you can see that there's no detected changes for the Mars file. And if I was to go and open it again, you can see that the ill-considered change is now gone. So that's basically, and now if I run git status, that the previously modified file is now no longer modified. So that's what you do if, so I use this command in practice if I'm coding something up, typically in Python, and I always make sure my code works before I commit any changes. But say I start working, I come in at the beginning of the day, I start working, and I break my script. It doesn't work, and I can't figure out what I've done. I've completely screwed it up, and I need to. I just want to go back to the version I had at the beginning of the day, and I haven't added anything or committed anything. I've just made changes. That's where this Git Restore command comes in handy, because it can just completely blow away the changes that you've made that have broken your previously working code and take it right back to where it was at the beginning of your session, say. So that's a really useful command. Okay. So let's say that we wanted to go back even further. So we have the current version of our file, and let's say we want to go back even further. Well, we could. Let's take a look and see if this Git Restore command works as expected. So let's do Git Restore H. Right. So here's the help menu for the Git Restore command. And so a file. So this looks like it's going to work a little bit differently than the Git checkout command previously did. So let's, in this case, we should revert to the lecture notes, because they will also work. So if we do Git checkout, and then we want, say we wanted to check out from the repository, not the most recently committed version, but an older version. So this would be the most recently committed. So let's try this one here. So if we did Git checkout, and then the start of the commit hash that we would need, and then the file that we would want to check out, we could do that. And now if we look at the mars.txt file, we've got, I need to clear this out. Well, what it's done is it's gone back to the version of the file here. Maybe the thing to do would be to just open the file. Yeah. So it's reverted it has taken the older version of the file that was in the repository and pulled it into the working directory. Yeah. And so basically, if we wanted to go back to a version of a file from whatever commit ago, we could reference this specific commit identifier and effectively pull it out of the .git directory and put it in our working directory. So now if we run Git Status, we can see that there is there are changes that we can commit, and if we want to unstage them, we need to run the Git Restore staged Mars text, like it says here. And then we'll close this and then open it again. And that should have taken us back to where we wanted. Nope, that's not quite right. We need to one more restore. And now, yeah, so now that's back to where we were before the ill-considered change. Okay. And all of that was because we hadn't actually added the ill-considered change yet, basically. So when we go back to the most recent version, we're basically going back to the point before we had made that ill-considered change. Okay. So let's go look at the teaching materials. There's a visual depiction of this process. So, here. So the head refers to the commit identifier of the most recent commit in the repository. And then these head tilde is just like referring to the previous, the one before that, the two before the head, and so on and so forth. And when you do this checkout command, you're basically going in and extracting an older version of the file or files and pulling those file or files into the current working directory. So another way is you can think of the .git directory as this kind of should I say, like checkout or check-in and checkout counter. And so when you add changes to the staging area, you then go to the checkout counter, and when you commit them, the checkout counter operator takes the staging area and puts it on the top of the stack. And then when you go and check out older versions, you go to the checkout counter and ask for a particular older version in the stack, and the the .git folder takes that version out and gives it to you and puts it in your working directory. Okay, so there are some exercises here that you can get some practice on, but let's kind of stop now for questions, and we'll give you an opportunity to kind of ask questions about this this whole process. So does anybody have any questions about this section on kind of going back and forth between different versions? No? Okay. Well, since there's no questions, then I want to just go ahead and move on. So I guess just to sum up, the two commands that we really looked at here were the Git Diff, which is how you use what the command you use to compare different versions of a file or files, and then this Git checkout and Git Restore, which is what you use to recover older versions of files. Okay, and I will make a note to actually update my teaching notes to use this new Git Restore command instead of the Git checkout, so that there's no ambiguity on that point. Okay, so this is a short episode on ignoring things. So oftentimes you're going to have files that you actually don't want to track, and they might be files that get regenerated often. Or they might be data files that are really large. Like, so Git is not well suited for storing like data files, files that aren't really going to change that often, so that are large. So you don't version control your CSV files or something, if those, or your .dat files or whatever format of data files that you use. You obviously want to back those up and you want to not lose them, but version control is not the tool for that. If you need backups for your data files, you can either work with Research Computing IT to back up and archive your data on Data Waha, or you can back up your data on your own, or by storing it on a file system here at CAUS that is automatically backed up for you. But you generally don't back up data files, but there might be other files that you don't want to track and version control. So how can we, so the best way to talk about how to ignore specific files is to create some dummy files. So let's go into our planets directory, and now we're going to create a directory called data, and we'll create a directory called results. And I think we'll put some files in there. So let's create some data files. So I'm going to touch in the data directory. I'll do a.dat data b.dat and data c.dat. c.dat. And then if I list the data directory, so we've got these 3 data files there. And then I'll do something similar in the results directory. So I will touch results, a.out, b.out, and c.out. So basically just creating these files. Let's look at what's in the results directory. So we've got these kind of data files and then these output files. And so now if we do Git status, so Git basically says we have these directories, data and files in the data file or directory and files in the results directory that aren't being tracked. So we don't want to version control these files. So how would we, the reason we don't want to version control, say, the data files is that generally they may be very big. So it doesn't make much sense to version control large files. And the results files, you might not want to version control the results files, because if you have your scripts that take the data and then generate your results, then as long as you're version controlling the scripts, you can generate the results from the scripts. This is a little bit less of a clear-cut case because if you're doing many different runs of experiments, then you need to have some mechanism for maybe managing the different versions or the outputs of each experiment. So you could do that with version control. There are other kind of domain-specific tools for managing experiments. For machine learning and data science workflows, there's something called 1DB, which is, or there's another tool called Neptune ML. If you have questions about how to manage your machine learning experiments and workflows, and we can talk about that. Git might not be the best tool for that, but you could certainly use Git to do something like that. There's a question in chat. So touch creates files. Yes, Renzo, that's what touch does. It just creates an empty file without opening it. Okay, so there is in order to ignore files, all we need to do is in our repository, we'll just create a new file, and we're going to rename it, and we're going to call it .git ignore. And this is a special file. It starts with a dot, so .git ignore. And we'll hit enter. Yeah, so we hit enter. And so now anything that we put in this .git ignore file, we can put patterns of file names and paths that we want to ignore. So for example, if we wanted to ignore the data folder and the results directory, or the results folder, we could add these folders there. And then if we save this, then we can, I'm going to clear this out. And the .git ignore file is just like any other file, so it needs to be version controlled. Oh, we also have this directory, this IPython checkpoints. So let's ignore that. So we will add that in as well, and I'll just kind of put things in alphabetical order. Okay, so now if we do Git Status, now notice these directories, the IPython checkpoints, the data, the results, they're no longer listed as untracked, but now we have this Git ignore file. So we'll just do git add.git ignore, git commit, added files to ignore by Git, or to added files that Git should ignore. Okay. And now if we do git status, so now we get the very simple on branch master, nothing to commit, working tree clean. So that's basically it. You have this .git ignore file, and you can put patterns of files that you want to ignore. So there are some exercises that talk about examples of if you have a directory structure that contains results data and results plots, and you only want to ignore results plots and not results data. Well, the pattern that you would put would be results / plot / so basically it would ignore everything that's in this directory, but not everything that was in the data directory. You could ignore all files that match a pattern except for a particular file. So anything that matches a pattern, like this is a common way is to say I want to ignore all .dat files or all .csv files except maybe a particular file. So you can basically put all kinds of patterns and things like that in this .ignore file, .git ignore file. But that's, and if you want to know how to do something very specific, you can hop on Google, but now you know what to Google for. So it's like, how do I add X to a .git ignore file? And then you'll find some Google will find you some answers on Stack Overflow or something like that. So I noticed a question in the chat about basically how big is big? And so I think Git has a per file max of like a few hundred megabytes, I think. But Git also has Git large LFS. So there is a plugin for Git that you can install for managing large files. And it's kind of trying to provide Git functionality for large files like audio samples, videos, data sets, graphic images, things like that, in a way that makes sense for large files that don't change that often. So you can install it. I haven't installed it on this JupyterLab extension. I might make a note to install it. That's one way that you can approach this problem. But basically, a few hundred megabytes is the largest file that you would want to consider version controlling. I only very rarely version control my data. In fact, the only time that I have done that recently was for a training course that I was giving on convolutional neural networks on using MNIST data. And I version controlled the MNIST data simply so that it would show up in the Docker image that I was using for teaching without having to have users download it ahead of time or download it during the workshop. So it was a purely kind of small scale pedagogical teaching example use case. Okay, so I think that's about all I want to cover here. So moving on. Okay, so here is the kind of the third of the big three episodes of content for today. So the first one was kind of the basics of the modify, add, commit cycle. The second one was about restoring older versions of files. And then now this is about working with remotes in GitHub. So in this episode, we're going to talk about how to share changes with others via remotes like GitHub. Talk about what remote repositories are and how they're useful, and then we'll practice pulling and pushing from our remote repository. Okay, so the basic idea, so you can think of, I like to think of remotes as serving two purposes. One is sharing code with others, whether they're your collaborators or research peers or colleagues. You can share, work that is in progress. You can share work that is ready for publication. It seems to be the standard in many of these major machine learning conferences that basically anybody who's submitting a paper to one of these major machine learning conferences will also have their code available on GitHub. That seems to have become the standard. Some conferences I know require that you make the code available publicly as part of the submission process to for the conference. Not all conferences are like this, but so that's one thing that you can use remotes for. The other thing that you can use remotes for is for keeping a separate copy of your work. So GitHub allows you to have an unlimited number of public or private repositories. So even if you have work that you're not ready to share with the world yet, by keeping a copy of your repository private on GitHub, that will allow you to always have a backup. So if your laptop crashes or you falls in a lake or catches on fire and you just lose everything that's on your laptop, if you use remotes and you are using Git effectively, and you are, as we'll see about what it means to push and pull changes, but if you are, at the end of the day, if you always push your changes up to from your local computer to your GitHub repository in the cloud, then your laptop can crash, catch fire, fall in a lake, or the Red Sea or whatever, and your changes will be safe. They'll be on GitHub. You can get another computer. You can clone the repository. We'll talk about what that means, from GitHub down to your local computer. And at worst, you will have lost a day's work. Or depending on how often during the day you push changes, maybe only a few hours worth of work. So all of my local repositories always have a remote repository on GitHub, whether it's public work or private work. Almost all of my work is public. Unless I'm working with a particular client who doesn't want that. All of my personal work and as much of my professional work as possible, I just develop in the open. Okay, so at this point, so you will need so I would encourage you, if you haven't already done so, to go ahead and open an account on GitHub. You will need an account on GitHub kind of for the rest of today if you want to participate in the hands-on portions of this, because we're going to be creating repositories and pushing and pulling and things like that. So the first thing that we're going to do, so I should say that a third reason that that repositories are really useful, or remote repositories are useful, is that it's a very effective way to move code from your laptop or your workstation to remote computing systems like Ibex or Shaheen. So if you can develop on your laptop or your workstation, and you can push your changes up to the remote repository in GitHub, and then you can have another version of that repository which is actually local to Ibex or local to Shaheen, and then you can just pull your changes from that you developed and tested on your workstation down to Ibex or Shaheen, and then you can run your larger job on those larger computing resources. Or if you're using AWS or Google, you can use this as well. So it's a very efficient mechanism to move source code changes from your development environment, which might be your laptop or workstation, to a remote computing environment where you're actually going to run your large-scale jobs. And that's, in fact, how I work. I develop on my workstation, sometimes my laptop. Rarely do I develop directly on Ibex. And when I've got everything the way I want it, I push my changes to GitHub. I then pull them down on Ibex and run my job. Okay, so the first thing we're going to do is we're going to show you how to create remote repositories on GitHub. So if I go to GitHub, and I need to go to I'll go to my personal GitHub account. So here's my personal GitHub account. You can see some of the projects I contribute to. And now to create a new repository, you go up here to this little plus button, and then you just click on New Repository. And if you have multiple places that you have permissions to create repositories, you would have a whole big list of things that you could create repositories. If you've created a new account, you'll just have, yourself, your own personal account. So here we'll create a repository called Planets. And we're going to make it a public repository. And then at this point, we can choose to create this repository with a Readme file, with a .git ignore file, or a license. We're not going to do any of those right now. So we're just going to leave those unchecked, and we're going to make it public. So now we'll do create repository. Okay, so now this has created a repository called Planets. And now we're going to link this remote repository with our local copy. And so Git has kind of given us some suggested commands to make that happen. So the first is basically a list of commands to create a new repository locally from scratch. And so you can see the suggested for that. But we've already done that, so we don't need to do that again. So actually what we need is just these two lines, actually. So we'll do, we'll copy this first line. So this git remote add origin. So it's going to add a remote with a name origin. And origin is just the conventional name for the remote on GitHub. And then this URL, which points to the .git directory for the GitHub repo called Planets. So we'll go over here to our command line, and we just paste that command and hit enter. Okay. So effectively, when we created the repository on the GitHub servers, it was kind of, you could think of it as if we had run these commands. We created a directory called Planets, we cd'd into the directory, and reran the Git Init. That's it. So now we have these two repositories. We've got our local repository, which has something like this. It has a bunch of commits, maybe a staging area, and some files in the working directory. And then our remote repository is just empty. So now we need to link the two up. And so that's what we're going to do. So we ran this git remote add origin. And so now if we run git remote -h, we can see that there is this -v option, which will just return the remote. So we can see if we've added it correctly, basically. So this should be the URL for our remote repository. And if there was a typo in there, you would rerun the same command, or you could rerun a command to fix the typo if you made a typo. Okay, so we've done that. So we've connected the two repositories up. And now we want to copy this third command, which is git push. And I'll talk about the -u flag in a minute. But it basically, this push is, except this should be master, because we want the name of the branch that we're pushing. So we're going to push the master branch from our local to the origin repository. And so we hit enter. And now it's going to ask you for your credentials. So at this point, you have to type in your username and then your password. And I must have mistyped my password. There. Now I did not mistype it. And so you can see this basically is some information about how much data is being pushed. And now if we go back to our remote repository and we refresh the page, we have, voila, all the files that we have. Basically, that now that Git repository is synced with the remote. So we can have all of our, well, that doesn't have anything in there. And then we have the most recent version of the file. And then we can walk back through the different commits if we wanted to. So basically the entire, not just the most, okay, so we did not just push the most recent versions. We pushed the entire repository history from our local repository up to the repo on GitHub. So now we have basically 2 complete records of our project. One is on our local machine, and one is in the cloud on GitHub servers. Okay. There's some other stuff here about again, the proxy service is not an issue that you should ever encounter. There's some stuff about password managers that if you want to click those links, it will explain how you can store your GitHub credentials so that you don't have to type your username and password every time you push changes to GitHub. And so now we're in this state. Basically, we have taken everything that is in the repository and pushed it up to the cloud. Okay, so just as we've pushed changes to the cloud, you can also pull changes down from the cloud. So if we were to try to run the command git pull, we just get this little warning message, which we don't have to worry about at present, and already up to date. So it basically, because there's no difference between the remote server and our local, or the version of our repository, the remote server, and the files stored on our local machine, then there's nothing to pull. There's no changes to pull down. Okay. All right. The GitHub Gui continues to improve. They all releasing new features all the time. GitHub was, I think, last year, was it last? Maybe slightly over a year ago at this point was bought by Microsoft. And since then, there's just been an enormous increase in the pace of like kind of new features and tools and things that are supported via GitHub. If you're a student, GitHub has a lot of free perks and things that you can get, and you just have to register. I think it's called the GitHub Education Pack. You can register for that with your with the .edu. Any educational domain from any country can register for that education pack and get a lot of free developer tools and resources, or access to software that might normally you'd have to pay for accounts for, things like that. A lot of stuff, a lot of integrations, plugins, third-party extensions for GitHub exist. They're typically free for open source projects. So any repository that's public, you can usually integrate these GitHub extensions for free. Going into GitHub extensions could be a course in and of itself. If that's something that would be interesting for you, you can provide that in the feedback to this course, and maybe we'll consider it in the future for future training on how to use GitHub effectively. I think that's about all I want to say about GitHub. Oh, I should say about license and Readme files. If you're going to share your code publicly, always have a README file. GitHub really tries to make you or get you to create a README file. In fact, why don't I do that now? So I will add a README file here on GitHub server. So they have a little text editor that you can go in here and say, well, so this is my project README file, which has a nice description of all the cool things that my project does. And so created a simple README file. And now I'm going to commit this change. So this is like you're running the, you're making the modifications. And then when you go down here and you put a commit message, then Git is doing a add and commit all in one go. And so now, if I go here, and now I do Git Pull, so again, we get this warning message. We don't have to worry about the warning message. It's just telling us that we can automate certain kinds of merge conflicts, which we haven't talked about yet. But then here, you can see that we've actually pulled down some data. We pulled down this README file. And so here is the README file that I just created on GitHub, and now I have a local copy of it on in my repository here. And if I was to look at, just clear this out, if I was to look at the log, so here you can see, here's me. Well, here's me on GitHub, which is different than the made up Vlad Dracula who had done all the previous commits. So that's my personal GitHub. Okay. And I guess I'm not super bothered about that being on YouTube, given that it's all over GitHub already. Anybody who wanted that email address could quite easily get it. So there you go. And the last comment about the license. So you should never put code publicly available on GitHub without a license. And if you have code on GitHub that does not have a license now, I strongly encourage you to check out the choose a license website, which is another GitHub initiative. I'll put a link in the chat. You can go through about what kind of license you want. They make some general recommendations. You know, if you are in the Python community, there's certain licenses that are very common in the Python community. You should probably use those. If you're in the R community, there are certain licenses that are common with the R community. You should use that. If you're not really working in a community and you want something that is simple and permissive, you can use the MIT license. If you care about anybody who takes your code and makes improvements to it also having to share your code, share their code, then there's a particular license for that. Choosing a license is a big topic. We'll touch on a little bit of we'll touch on the trade-offs in a little bit, but you should always put a license with your code if you're making it publicly available. The reason for that is if there is no license, then it's effectively public domain. You are not giving up copyright. Like even if you publish it without a license, you still retain the copyright over the material that you've created, but you know, anybody could basically use that and not have to attribute the fact that it came from you. And there are a whole host of issues that could come up with that. So always, always, always put a license on code if you're going to share it publicly. Okay, so that's it. So we talked about GitHub. We explained how to create a remote repository on GitHub. We talked about we showed how to link up that remote repository with an existing local repository. And then we showed some examples of pushing and pulling between local and remote repositories. Okay. So moving on. So collaborating. So this episode, so there's a question in the chat. So if I'm not mistaken, GitHub doesn't provide a DOI for the repositories. I guess always needs to be done via services such as Zenodo. So yes. GitHub does not provide digital object identifiers, DOIs, but you can get them from services such as Zenodo. So this is an initiative that came out of CERN. So all the billions of dollars that have been put towards building the next largest, biggest particle accelerator and super colliders, some of it gets used to do things like create Zenodo, which is an archival data and source code service. So they have some mandate that they have to archive all of their data and source codes and things like that for the CERN project for some number of decades, I think. And Zenodo is the service that they created to serve that purpose. And they've opened it up to the public so that you can use it to archive your own data and your own source code and get a digital object identifier. So they have, you can integrate Zenodo with GitHub and automate the process of generating a digital object identifier for each release, each new release of your code. If you're developing a project that, if you're just developing a project for a particular paper and that's kind of the end of that project, then you would have one DOI associated with the source code. And then you could cite the source code in your own paper, and you'd have a separate DOI probably for your paper. If you're working on a project that had many releases and was, over many years, then you would probably have a different release for each, or a different DOI for every release. And this allows, new contributors who come in, who maybe didn't contribute to previous releases, they can contribute to this new release, and they can have a DOI that they can use to get build citation counts and things like that. So thank you, Anthony, for bringing that up. Okay. So collaborating. Whew. So we're getting on towards the end of the day. I feel like it would be a good time for another break before we dive into another kind of meaty episode on collaboration with GitHub. So let's take a 5-minute break, and then we'll come back. So it's about 3:45. So we have a little over an hour left, and we need to cover collaborating. So this episode and the next episode are the really important ones, and then the last bits are about kind of philosophy of open science, and we'll touch on some of these issues that we've talked about already, but in more detail. Okay, so let's take a 5-minute break. So I'm going to stop sharing and pause the recording, and then we'll come back in 5 minutes, and we'll pick up with the last two kind of big content exercises on collaborating and then dealing with conflict. And then we'll kind of end the day with a more lightweight kind of discussion and Q&A on open science. Okay, so I've paused the video or pause the recording, and I'll be back in 5 minutes. Okay. So we're back. Nice short break. So before I start recording again, I need to test something. So I'm going to share my screen. Now I'm hoping that you can see a web browser, but then also this little terminal over here. And this terminal is my terminal on my my local computer, basically, where I'm teaching from, not the Jupyter lab in the cloud, obviously. So can I just get, can you go into the participants and just check check yes if you can see? I just want to make sure that you're seeing what I think you're seeing. Okay, cool. All right, thank you. That's very helpful. All right, so I'm going to stop sharing. Right. Okay. Huh. Looks like I forgot to pause the recording while we were on break. So it'll just be a nice 5 minutes of just dead blackness in the middle of this recording on YouTube. So, oh well. Okay. So we're going to pick up with, I guess I should go back to sharing my screen again. So we're going to pick up with collaborating. So in this episode, I'm going to talk about how to use version control to collaborate with other people. We'll walk through the process of cloning a remote repository and talk about collaboration by where everybody, all of the collaborators share a common remote repository on GitHub, and then they push to that common repository, and then pull changes from that common repository. So it's going to be a little bit of an experiment. Frankly, when I teach this in person, I have everybody kind of pair up and do and kind of go through this episode together in pairs, where one person is the owner of the repository and the other person is the collaborator, and then switch and then practice in the opposite direction just to kind of understand the mechanics. I was a little bit worried that could go horribly wrong in such a large group like this. So instead, what I'm going to do is I'm going to be me. I'm going to kind of split myself into two people. One person is going to be, is going to be me and my personal GitHub account, and the other person is going to be Vlad in Jupyter Lab, and then I will show you how this would work. All right. So I think there is a question in the chat. Yes. So the question is basically, will you share the account later on? Yes, I will. I will share the link to the KVL YouTube account in the email that you will receive tomorrow, which will have a link to a feedback survey that I would like you to provide feedback on the course today. So you'll have it. Okay. So basically, I'm going to demo this, and hopefully you'll get the idea. Okay. So normally the first thing that you would have to do is, if you're the owner of a repository, then you will need to add collaborators, and your collaborators will need to have an account on GitHub. And then these screenshots kind of walk you through the process of going to settings and then adding a collaborator and inviting them to join, and then they will get an email and they will need to accept, and then they're added, and you can manage access and permissions on what they can do, what they can and can't do to the repository. Okay, so then once you have a collaborator who has accepted to be a collaborator on your project, that collaborator will need to download a copy of the repository on their machine. So on my local machine, I'm going to change to my desktop, and then I am going to clone this copy of this repository from the remote on GitHub down to my computer here So to do that, you click on this code, and there are two options for cloning. One is using just HTTPS or SSH. And now there's even a GitHub command line interface for cloning. For now, I'm just going to do HTTPS because I don't want to talk about SSH and SSH keys and key generation and things like that. So I'm just going to select HTTPS and click this little clipboard to copy this URL to the clipboard. And then I just do git clone, and then the URL to the remote Git repo, and hit enter. And what this will do is it will create, my desktop, it will create a directory planets. And inside that directory is just the contents of the GitHub repository. So now I've used this clone command to create a copy of the repository from GitHub locally on my computer. You can also use this clone command to create a copy of a repo from GitHub on Ibex or Shaheen. It's the same command, git clone and then the URL, and then Git will go out and download the repository onto that server, basically. Okay. So now we've done that. And so now we kind of have three copies. So we have the original copy here. Make this a little bit bigger so it's not so squished. This way a little bit more. So we've got the original copy that we have been creating. I'll clear this out. And I'm gonna get rid of that. Where my username is Vlad Dracula, and then we have over here where I'm just me. And so these are going to be the two kind of collaborators on this project. And in this case, you can think of me, I am the collaborator and Vlad is the owner for all intents and purposes. Okay, and it would be the same if we had even more collaborators, they would go through the same area. Okay, so now I am going to be me. So now I'm using the terminal on my machine. I am going to create a file called, I guess I need to change into the planets directory first. So I'm just going to use the nano text editor to create a simple file called Pluto. And then I'm just going to put some content in here. So I went through that quickly. I don't want to get derailed by how to use nano, but basically I've just created I've created a simple text file. And now I'm going to do git add Pluto, and then git commit, and added notes on Pluto. Okay. So now I've added an extra commit. This commit does not exist in the GitHub repository. It does not exist in the local repository for Vlad, my other collaborator. It only exists on my local copy of the repository. Okay, so now I can git push origin master. So I'm going to push to the origin, which is the GitHub repository, any changes that are on my local copy. Okay, now if I come over here to GitHub and I refresh, we'll see here's this file that I had just created. So I created this on my local computer here, and then I pushed it, and you can see here's me, all about me, added this note. So this was the commit message that I just typed, and this is the commit hash. You can compare these 7 digits to these 7 digits here. So that's the most recent commit. Okay. But note that it does not exist here. So this doesn't exist here on Vlad's copy because Vlad hasn't pulled those changes yet. Okay. So there's some commands, some discussion. I don't want to go into the details of all of the other Git remote commands, but there's commands for adding and removing remotes, which we've talked about, and commands for changing the URL or renaming, changing the URL if you need to for an existing remote, or renaming a remote, things like that. Right. So now, if Vlad wants to get these changes, he needs to pull them. So if he runs a git pull command, so you can see here in the summary that this Pluto.txt has been pulled down. And then if I just wait a little bit, now I see I've got this Pluto.txt here. So that's an example of a workflow where you have you and your colleagues are making local changes and pushing them up to GitHub, and then you pulling down each other's changes. And as long as you're working on either different files or parts of the file or different parts of the same file, then you can just push and pull like this and go along your merry way, and everybody can make progress on what he or she is doing, and without running into problems, and they can collaborate that way. As you might imagine, the chances of somebody editing the same part of the same file and you running into conflicts is pretty high, and we're going to talk about how to deal with that in the next episode. But that's kind of the basics of this collaborative workflow. So you're going to make changes on your local copy. You're going to stage those changes with git add. You're going to commit them with git commit, and then you're going to push them up to the remote repo with git push. And then your collaborators and you yourself will pull their changes with git pull. And you just kind of go through this again and again and again. Okay. And then, of course, we covered the git clone command to create a copy of a remote repo on your local machine. So Anthony has a question. So git pull almost never works by itself on my Linux PC. It needs to be preceded by git stash save. So yeah, so the reason is that you probably have changes to files in your local copy that would be overwritten if Git allowed you to just pull in things from the remote repository. So you would either need to restore your local copy of those files to their most recent version, or you would need to add and commit those changes before pulling. So that's what's happening. So you have changes on your local files that would be overwritten by a pull. And I might be able to concoct an example of that in the next episode, and we can go through it together. Good question. Okay, so I'm going to move this over here. And okay, so the next episode on conflicts. So what to do when your changes conflict with someone else's. So the objective of this, that's the question that we want to answer in this episode. So the objectives are to give an explanation of what conflicts are and when they can occur, and then talk about some automated ways in which you can resolve conflict with Git, and then ways in which you need to have a human in the loop. And at some level, resolving conflict is it is a human process, and definitely is going to require collaboration and discussion with your research colleagues. Okay, so let's see what we mean by this. So I described this process of kind of pushing and pulling local changes, or pushing local changes to the remote on GitHub, and then pulling down others' changes to your local copy. And almost as soon as you start doing that, you're going to create conflict. People will change files on you that, or change the same file that you're on, same sections of the same file, this kind of stuff. So it's going to happen very quickly. And the nice thing about version control systems like Git is that they provide a rigorous process for identifying conflict and for helping you to resolve that conflict as painlessly as possible. And they're much better than alternatives where you basically have to send a document back and forth via email. And in the email, you try to basically describe the changes that you've done and describe why you changed it. And then resolving conflict in that way is very time consuming. So, let's create some conflict. So on my local copy here on my computer, I am going to edit the Mars file and likes to create conflict by writing really aggressive and unsupported assertions. How about this? I'm just making unsupported assertions. There we go. So I like to make unsupported assertions. So I'm going to save this. And then I need to git add and commit added an unsupported assertion. And then I'm going to push these changes to GitHub. Okay, so we'll come over here to GitHub. And we can see that this mars.txt file changed 16 seconds ago. And there's my unsupported assertion. Now, Vlad, on the other hand, is going to open his mars.txt and write a really well-supported argument. And then I'll use the GUI interface this time. So if I come over here, go to changes. So here's Mars with a change. So I'm going to add that change. And then now it's staged. Now add commit message, added good point. Added well supported assertion. Commit. Okay. And now I can look in the history and I can see, okay, so I have this here. And now I want to push. And I'll show you actually here, there is, well, I should do it from the command line first. So now I want to do, so git push origin master. And now you put in my credentials. and I get an error. And the reason is that there are changes on the GitHub repo, the GitHub version of the repo, that are in conflict with the changes on my local. And so now I have a conflict, I need to resolve it. And it's basically saying that before you can push, you need to pull. So I will do git pull, and then the pull, I have a conflict. And basically Git automatically picks out that it tries to auto-merge this mars.txt file, and it detects a merge conflict in mars.txt. The merge has failed, fix the conflicts, and then commit the result. Okay, so now what Vlad can do is can open mars.txt. Now, notice the way that Git has marked up this file. So it has this change, which is the head of my local repository. So this is my change. This is me, Vlad. This is Vlad's change, his really well-supported argument. And then there's the change that was coming from the remote repository, which is David's unsupported assertion. And so what it means to resolve this conflict is for either, Vlad and me to get together and decide either which of these versions should we use, or if one person has kind of the authority to make that decision, then that person could decide. So there's some kind of human process that has to be done to resolve this conflict. It's actually, if you look at a lot of the issue trackers and discussion around GitHub repositories, a lot of the discussion is basically about figuring out how to sort out these kinds of conflict, basically. But let's suppose that we don't really like unsupported assertions in our paper or in our discussion, so we're going to get rid of my unsupported assertion and leave in Vlad's really well-supported argument. So we make those edits, we save them, and now we need to add and commit the result. So we will do git add mars.txt and git commit. Now I really need to reorganize my my screen a little better. Just make that go away. Commit message, and then a commit message can be fixed merge conflict in favor of Vlad's well-supported assertion, something like this. And then we can do Git Status. And you can see that I'm on the branch master, and this this local version, so Vlad's local version, is ahead of the master repo by 2 commits. So I need to push these changes. So I've resolved the conflict, and now I need to push the changes. Back to GitHub. Yep. And now I, as in David now, as the collaborator, can pull, and notice that now my pull doesn't have a conflict. And that's because the commit that resolves the conflict has been added to the repository, and that can just be layered on top of my previous commit. So if we look at the Git log, we'll see, so we have, this is the unsupported assertion, and then there was the well-supported argument that Vlad added, And then there was the merge commit, which merged the conflict in favor of Vlad's. And then if I look at the Git log here, it's the same Git log. So previously I had added this, pushed this unsupported assertion, but now Vlad has resolved the conflict by adding these 2 additional commits. And so I just pull down those local changes. Okay. So the first time you go through that process, there's a lot to kind of understand. And as you're getting started, you're probably more likely to be using Git to version control your own project. So you're not going to have too many conflicts unless you create, in some sense, like internal conflict. If you make changes locally and then also go into the GitHub UI and make changes on GitHub directly, and then you can create a bit of a mess. So I would discourage you from doing that. You know, just develop on your own local repository and just use the remote as a duplicate copy of your own work if you're working with. Excuse me. Okay, so this is kind of just a graphic of resolving the conflict. You have, you know, one person makes changes, another person changes the same document in the same place, but with different changes. And then how should Git order these changes? And there's no unambiguous way to do that. So Git will say, up, you know, we've got a conflict. You need to resolve the conflict before you can merge. And that's, you know, we walked through an example of how to do all of this just now. Okay. Right. So key points. So whenever 2 or more people change the same lines in the same file, you're going to create conflict. Changing the different lines in the same file is not a problem. Git can automatically merge that for you without you having to get involved. A nice feature about the version control system is that it does not allow you to overwrite changes blindly. Git is very good at identifying conflict and highlighting those conflicts so that you can resolve them either by, you know, going and having an internal discussion within your research team, or more recently, a lot of projects are basically that discussion goes on GitHub. So, you know, if we come back here, you know, the concept of pull requests is a little outside the scope of forks and pull requests, and things are outside the scope of this course. But just as an example, if we were to look at let's look at PyTorch maybe. So PyTorch, their GitHub repository. So there are 30,000 commits in this repository. There are over 5,000 outstanding issues. So these are either bugs or issues with things that are not working as they should, or requests for updates to documentation, things like this. So these issue trackers are where people organize a lot of this discussion around, you know, improvements that need to be made to the software or to the repo. And then pull requests are how people actually provide solutions. And it's these solutions, potential solutions, that might generate conflict. And in the, let's just pick one of these. I don't know, this one. So in this pull request, there will be a discussion thread which would contain the discussion around how to solve any merge conflicts that might come up as part of the process of merging this pull request, which solves some particular problem, into into the main PyTorch code base in this case. And as you see here, so a lot of things can be automated. So these are all GitHub extensions that automate various portions of either tests or other things. Those are all, again, advanced topics that are outside the scope of this course. But the point that I want to get across is that a lot of this human process of resolving conflict via Git and version control systems is being increasingly done in public and online. And which is nice because then you can have collaborators that can be located wherever, and you can have these kinds of conversations in a way where it's being documented and captured. And again, all of this can happen for private repositories as well. If you, it's not, you don't have to do all of this work in public. You can still do it in private on GitHub. Right. Okay. So any questions about that? I'm gonna stop sharing momentarily, but then any questions about resolving conflicts? I would say the best way to get comfortable at resolving conflict is to create like what I've done here and demoed for you. You should do it yourself. Just like, you can use the Binder Hub repository like I've been using it here. You can create another repository. You can kind of create contrived conflict and just practice resolving it. Just as in real life, you're not going to get better at resolving conflict if you don't practice. So, okay, moving on to open science. So at this point, I've covered the bulk of the technical material on Git. The last part of this workshop is going to be about some ideas on open science and collaboration and resources and things like that that are useful to make you aware of. And I'll probably take about 15 minutes to move through this material, and then we can have, if there are any questions, we can do Q&A. Otherwise, we'll probably be out wrapped up around 20 minutes from now. Okay, so I'm going to share my screen again. Right, okay, so open science. So the question is, how can you use version control to help make your work more open? And then the objective is, again, to try to tie in the concept of version control, whether it's with Git or with anything else, to this idea of an electronic lab notebook for your computational work, whether that is traditional HPC style computational work or machine learning or data science type work or bioinformatics or however you would classify your computational work. Right. So in some sense, free sharing of information is some kind of ideal that we try to aim for in science. It is why people publish results in journals and conference proceedings, and we try to share our work as much as possible. But when you actually start digging into the details of what this looks like in practice, it's usually a bit more muddy. So you're going to collect some data, and then that data is going to get stored on a machine that is probably not managed by you. It might be managed by your university IT department. That server might be backed up or not, depending. So then after you've collected this data, you're going to write some small programs. These programs are probably going to live on your computer. They're going to analyze that data. You're going to generate some results, write them up, submit a paper. The journal may or may not require the data to be submitted in order for your article to be published. Increasingly, that's the case, but not always. Very few journals have journals or conferences have hard rules on submission of code used to obtain the results. That's changing. most of the major machine learning conferences have some requirements on submitting the code used to obtain the results in the paper, but anybody who has ever tried to pick up a NeurIPS paper and try to replicate it based on what is written in the paper will know that that's basically impossible. And if you try to use what's written in the paper and then actually the source code that is provided on GitHub, that's still often impossible. So there's a lot that is a lot of room for improvement, basically, in these kind of in these areas. So eventually, there is going to be a paper that will be published. There might be a link to an online copy of the data. The paper might be behind a paywall. It's sometimes easy to forget. Those of us who are, at universities and in academia, we go looking for papers online, and we just find them because as long as we're on the KAUST intranet, then most of the journals detect that, oh, KAUST has a subscription to this journal, and therefore you can read the paper from this journal. But if you're not, then you very quickly realize that most research published at universities is not, the final product is often not publicly available, even if it's been paid for by public research funds. So that is changing, and there's some links here to some resources that are increasingly being used, and I would want to make you aware of if you're not already aware of them. So you can take your data that you collect and store it in an open access repository where anybody can access that data. So Figshare is one. Zenodo we already looked at, but these are online repositories of data. You can store your data. Zenodo typically accepts very large data files because they're associated with CERN and they have a mandate for that. Figshare is for usually smaller data sets, but you can get a DOI for your data set. And so individuals can cite the data independently of the paper. Dryad is another resource for data sharing in that capacity. You can store your source code on GitHub. You can get a DOI via Zenodo or other sources for your source code on GitHub. People can then cite your source code independently of your paper, which will have its own DOI. Preprints on archive. So depending on what domain you're in, you may be well familiar with archive or you may not be. My graduate work was in economics. We didn't have anything like archive. So when I kind of moved away from economics and I came across archive, I'm like, wow, this is fantastic. I wish we had had something like this when I was doing economics research. So there is a kind of growing body of meta-analysis that work that is more open is more widely cited and more widely reused. So if you want to have impact, then it behooves you to adopt a more open, collaborative, sharing-focused workflow, I guess is what I would say. And there's some links here to some more resources on both on the evidence about work that's more open, being more widely cited and more reused, and also different aspects of open science. There's a whole book, a book written on that. And then there is some other resources. So, right. There's some thought exercises here. Take it, it's pretty late in the day at this point, but I would encourage you, when you have some time, sit down and think about how reproducible your workflow currently is. What are the chances that someone in your own, if you work in a research team, what are the chances that you could just give your code to someone on your team and they would be able to reproduce the results in the most recent paper that you did? And then if the answer to that is, yeah, I think my teammate can do it, then you could ask, well, what are the chances that, you know, a very technically knowledgeable person in my field could do it? And then continue to expand the circle until you know, and have a good think about really how reproducible it is. You know, what are the chances? You know, you should pick some reasonable target and say that, you know, I want, you know, if I'm submitting a paper to NeurIPS, then it should be the case that a technically knowledgeable person who is also attending and submitting papers to NeurIPS should be able to reproduce my results. And can they do that now with the current workflow that I'm using? It's a good question to ask. If you've not used one of these data repositories, I would encourage you to take a look at them and consider using them on your next project. You know, this may require some discussion with your PI if you're not a PI, in terms of what you know, what maybe rules and regulations might apply to your particular kind of research data. You know, these things differ. And there's also a link. I mentioned the large file storage earlier, but there's a link to there's another link to that in the notes. Okay, so I think I'm just going to kind of push through these 3 episodes as a block, and then we'll do one large Q&A about all of this at that point. So the next episode is about licensing, and I mentioned licensing earlier and the importance of putting a license with your code if you're going to share it, online. So there's a link here to the choosealicense.com, which I shared with you earlier, that has some good good resources and good kind of defaults depending on what you want to do. So important things that you want to think about when putting a license you know, online is, you know, is the software patentable? Do you care about patent rights? Do you want to require people who are going to build on top of your work to also distribute their source code and make it open and available for everybody else? Or do you not care? You know, what is the content that's being licensed? Is it source code or something else? Because what I'm mostly talking about here is licensing source code. If it's something else, then, you know, you need to go and consult the relevant resources on whatever it is. You do need, if you're going to put source code on GitHub, you do need to put a license with it. That's the big thing I want you to take away. Please do not put source code on GitHub that does not have a license. It either makes it so that somebody who comes along and really wants to use your source code, they may not use it. They may not cite it because it doesn't have a license, because there's no, if they're principled, they may come across it and say, well, there's no license here. Therefore, I don't really know what I can and can't do with the code. So I'm not going to cite it. I'm not going to build it or use it in my own work, even though it might look very good, because I just don't know what's okay and what's not okay. If somebody who's not principled comes across it, they might just take it and use it and not give you any credit for it or any or anything like that. And neither of those are a positive outcome. So the first question that you need to, I guess, resolve is, you know, whether or not you can use an open license. So, you know, for my code that I produce here at KAUST, you know, from within the core lab, you know, the copyright is attributable to myself and KAUST. And then the license, you know, we can use any of the standard open source licenses for the work that we do here within the core labs. You know, if you're outside of the core labs, or you are, you know, with a PI or things like that, like these are questions that you should discuss internally before, you know, just chucking code up with a license. You probably do need to have a discussion with either your PI or your institution or things like this about what licenses you can and cannot use. It's always a good idea to use an existing license. So the choosealicense.com has dozens of existing open source licenses. Do not try to write your own license that says, well, I think that my code should be used for this and not these other things. You know, you're not a lawyer. These are very legally delicate issues, and the existing open source licenses have have track record behind them. They have gone through litigation in many different countries under many different legal systems, and they're kind of tried and true, and you should use one of these existing licenses. So that's the takeaway from that. Okay. And I think, is this the last? Almost the last. Okay, so finally, citations. Good idea to just chuck a citation file or a citation.txt file into your GitHub repository that explains exactly how you want that software cited. Might cite the software itself because it has a DOI from Zenodo, or you might want to just cite a paper that's been written and published about the software itself. So, you know, make it explicit what you want others to do in terms of citing your code by putting this file in your GitHub repo. Increasingly, crawlers are crawling GitHub and looking for these citation.txt. I think Google Scholar will do this. It will crawl around GitHub, and if it finds these kind of citation.txt files, it will use it and its own internal algorithms that are used to build Google Scholar pages and things like that. So by sticking a file like this in, you might be able to bump up your citation counts from some of these automated citation tracking algorithms and things like that. There's a link here to Software Sustainability Institute, which is a great resource on these kinds of topics: licensing, open software development. A lot of resources on how to maintain. If you're a PI today, and you have a lot of software that's created within your group, and you want to think about how can I develop and maintain this software as my researchers come and go, then the Software Sustainability Institute is a great resource on kind of how to do that in an effective and sustainable way. Okay, finally, hosting. So this is basically like, do you want to use GitHub or something else? There's GitHub, GitLab, and Bitbucket are the kind of the three big ones. It seems like almost everybody is on GitHub for sure, and then possibly other projects on GitLab or Bitbucket. Big projects are often hosted on all three, like GitHub might be the major one where all the development is going on, and then there are mirrors on GitLab and Bitbucket. That is probably overly complex for most of you. I'm on GitHub. All my stuff is on GitHub in one place. I don't imagine using GitLab or Bitbucket. Calst has an enterprise account with GitLab. I do not believe it has an enterprise account with GitHub, although you could contact IT Research Computing to ask, but I know that they have an enterprise account with GitLab. This would be relevant for you if you work with source code repositories that need to access sensitive data that simply for legal reasons cannot reside anywhere than on Calst servers. And that might mean that source code that is related to these projects can't also need to reside on Calst servers. In that case, you'd probably be using GitLab because it has tight connections into the research computing IT infrastructure. They will have, I think they have their own training on Git that is more focused on GitLab integrations and things like that. So you might want to reach out and ask IT research computing about those kinds of issues. I think that's all I want to say about hosting. So if you're just getting started and all of these kind of complexities are lost on you or feel like they're a bit too much to think about, just set up an account on GitHub and get started there, and then you can worry about these extra details later. I think so. That's it. So this last episode is about RStudio, which isn't relevant for the well, if you are interested in how to use Git with RStudio because you use R, then by all means, please go through that episode. It will explain a lot of how to do the things that I showed you how to do with JupyterLab and Git, but with RStudio. Okay, so I'm going to stop sharing my screen now. So does anybody have any questions about anything that we have talked about today? So the question, any advantages of using Bitbucket over GitHub? None that I can think of. Bitbucket has been around for longer, I think, than GitHub has. GitHub got an enormous amount of network effects because they tried to basically take Bitbucket, but then bolt kind of a social networky kind of aspect on top of it that Bitbucket didn't really seem to have. And that really took off. It proved to be a winning combination. So source tree. So Laurent has a question about source tree to visualize what people do in collaborative projects. Do you recommend it? I have no opinion on it because I don't know what it is. So I'm just going to Google for it now. So, okay. So it seems like it's a tool that connects with Git repositories to try to track maybe issues across multiple Git repositories or projects, something like this. Is that roughly the idea, Laurent?
Yes, so you can visualize. So on the web page of source tree, you see this graph with colors. Okay. You can visualize the different paths of when people pushed something.
Okay.
Pulled.
So that's very interesting. So I was aware that there are many kinds of solutions for this. This is a very common problem, and there are many solutions for it. Source tree was one that I wasn't terribly familiar with. I think I'm just going to do a check. I think GitHub has. I feel like GitHub has some built-in support for this already, but I can't. It's exactly the right Google combination is escaping me at the moment, so I can't find the link. But I'll look for it and try to share it if I can find it. But I know that there are many solutions, and I don't really have a strong opinion about any of them because I haven't used too many of them myself. So there's so GitHub Desktop. So GitHub does have a. I should mention that. So GitHub Desktop. I'm going to share my screen again. So thank you for bringing up. So GitHub has a desktop client. So the way that I've showed you how to use Git today is basically using Git from in JupyterLab. And that was simply for convenience purposes. It was easy for me to give you access for teaching through a terminal window to use JupyterLab and to demo some of the JupyterLab integration with Git. There are many kind of graphical user interface clients that try to make it a little bit easier to get working with Git without having to type all the commands all the time. So learning the commands is useful because it helps you understand what's going on. But I would encourage many of you to take a look at one of the many GUI clients for Git, many of which will have really nice integration with GitHub. and it will kind of simplify, make it easier for you to adopt Git in your own work and in the work in your lab. So there's GitHub Desktop. So that's like GitHub's supported client. You can get Mac, Windows, Linux, possibly, probably. There's also another one called Git Kraken, which I played around with at one point, thought it was really nice. It's the most, I think, one of the more widely used and popular ones, and has also a kind of a slick name and things like that. So I would encourage you to take a look at, so I'll put these links in the chat. Some links to GUI Git clients. So there is the GitHub Desktop, whoops, and Git Kraken. Okay. Any other questions? Nope. Going once, going twice. Done. Okay. Well, thank you very much for spending this Tuesday afternoon with me. Git is one of the more challenging tools that we teach as part of this Introduction to Data Science workshop series. So if you felt a little lost at times, or you felt like it was a bit confusing, I was right there with you when I first learned to use Git. It is worth the effort. Since I adopted Git and started using it as part of my research workflow, I have never lost work. I have been able to share my work more easily with my research colleagues around the world. I have been able to contribute to open source data science machine learning projects like scikit-learn and Horvath, which has really boosted my profile within the machine learning, the global kind of machine learning and data science communities. And so it's really been worth, for me, it's certainly been worth the effort. But it did require some effort. I will not lie. Okay, so the recording will be available on YouTube. I should remember to, I guess I will pause.